Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. So yesterday I gave a very boring lecture with all the JSONic and so on and so on. And today we'll dive into the physical implementation of it. So no more details on the syntax of JSONic whatsoever. All right. So I just wanted here to say that with JSONic, it's very easy to create CSV or Parquet file. You already have everything you need to know. You know JSON, so you can create schemas like this. And then you can use the command line parameters to say that you want CSV as output, that you want only one partition, creates only one file, and that you want the headers. Then it's beautifully opening up in any spreadsheet software like this. Then you can use matplotlib or whatever other libraries you want, right? So it works with plenty of formats. Okay, so the physical implementation. So I was asked, and this is a common question to ask, what is the difference between JSONic and Rumble? And how does it connect to Spark? So this is, in fact, the goal of what I want to explain today. So the difference between JSONic and RumbleDB is that JSONic is a language, like JSON, like SQL, like Java, like C, like C++, like Python. So this is a language. A language is just a way you interact with a computer, but it's not an implementation of the language. And RumbleDB is the implementation of that language. So you know that you can either interpret or compile a language, but there is a difference between a language and an implementation. So JSONic is the language, RumbleDB is the implementation. And it implements JSONic on top of Spark, but that's what I will explain now. So all this work here has been the work of many students over the years. So currently Marco in his master's thesis, and the architecture is actually quite a standard compared to many other querying engine. We have this incoming query, and the first thing we do is we parse it. Who took a compiler class, compiler BAO? Okay, so everything you learn in compiler BAO, this is where it goes. You write a grammar, you have an EBNF. This is the standard form of having the grammar of some language. And then there's libraries for that. And then you get an abstract syntax tree or AST. Who has already heard of AST, abstract syntax tree? Okay, great. This is all modular. So here we didn't invent the wheel. We just used G4 or NTLR in order to do that. Okay, but the abstract syntax tree is only the first step. Then what you need to do is convert this abstract syntax tree that is very close to the syntax to what's called an expression tree. An expression tree can be seen as some cleaned up and tidied up version of the abstract syntax tree. So in the expression tree, you have all the expressions of the language, but from an abstract perspective. And I told you last time I counted it in terms of Java classes, there's 37 expressions, right? So additive expression, multiplicative expression, variable expression, all the literals, FLWOR expressions, if then else expressions, and so on and so on. So 37 of them. And so what you do is that you convert the abstract syntax tree to an expression tree. This is done with a visitor pattern. Who already heard of the visitor pattern? I hope many of you, yeah? Awesome. So visitor pattern, you visit the abstract syntax tree and you output an expression tree. And this is beautiful. This is my favorite part because here it's a beautiful mathematical high-level representation of your query. And I insist on representation because at that point there is absolutely nothing that is evaluated or executed. This is just a tree that has the content of the query. And it's typically at that point that you do a lot of optimizations. So I can give you a few of them, the sort of things that is done at that point. You can rewrite some inefficient formulations in the language. In fact, one of you pointed to a beautiful example of that. This is for where, when you have a join, where you have for blah, 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 for blah, 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 where blah, blah, blah. This is typically the point where you automatically detect the join and then you modify the expression tree to make it explicit that it's a join. This is the sort of things that you can do. What we also love to do at that point, not just RumbleDB, but many engines, is to try to detect the static types. Because you probably noticed that you don't need types in JSONic. You can put them, of course, but you don't need them. And typically, an engine is going to try to detect the types. But I insist on static types, because you don't execute anything. You just, at compile time, try to infer the types of the things. And that allows you to do optimizations. For example, there is one optimization that I will discuss. What is the type system in JSONic? It's all sequences of items, right? So it's a type system that is based not only on atomic, object, integer, and so on, but also on cardinalities. You have the empty type for the empty sequence. You have a type of exactly one, cardinality of exactly one integer, exactly one string. You have a one or more cardinality with plus, right? Integer plus is a sequence of one or more integers, and star is for 0 or more. That we covered in the validation and data modeling lecture. But why am I saying that? Is that at compile time, for example, if you see an addition plus, then you know that what's going to come out of that is either 0 or 1 item, but you're never going to get 2 items out of an addition, right? 0 or 1. And that is super important information, because the moment you know that an expression is going to return 0 or 1 item and not a billion, then you know you don't need Spark for that. So as soon as you detect it's just 1 item, that you can do locally on the machine. For whom does that make sense? Right? And if you detect it's a huge sequence, could be billions of items, then you will spread it over the cluster and parallelize it. Right? So I'll come back to that. This is the time where you figure these things out, that you just look at the program, analyze it, and try to deduct these things. All right, so there's plenty of other optimizations that are done there. And then comes the big moment where you convert this expression tree to a runtime iterator tree. This is the part that is executable, that you can actually trigger, you press a button, and then it evaluates the whole thing. Again, it's a visitor. You use a visitor, and the visitor is going to output a runtime iterator tree. It looks very similar in structure. This is why we use the visitor, except that these iterators, they're not just an abstract mathematical representation. They actually contain the execution codes that is able to compute all the results of the queries. For whom does that make sense? All right. This is very typical. This is not specific to RumbleDB. You will find most querying engines have exactly that sort of implementation, right? Even PostgreSQL or even any database engine. So this is pretty standard. Now, if we focus on the runtime iterator tree, because now I would like to tell you how it's actually executed, what actually is going to happen in your cluster or on your laptop. These iterators that you see here, they are called iterators because from a naive perspective, on the, if you don't think of parallel execution or anything, when you have sequences of items, your first idea is typically going to use the iterator pattern, the Volcano iterator pattern. Who heard of that? Right? So let me tell you, because not all of you said yes. It's when you have an API that basically has methods such as open, has next, next, and close. Who already saw that? That you saw, right? So this is typically an iterator. In fact, they are so used and so all over the place that in Java they are even handled natively with just a colon. You can iterate implicitly without even having to call them, because this is very common. And so indeed, one way to execute a query like this, that is in the form of a runtime iterator tree like that, is that you go at the top over there. That's basically the outer of your query, and this is all the inner part of the query. And when you put yourself here, you basically call open, has next, next, has next, next, and you just pull the items. It's a sequence of items, right? So you pull the item one by one, right? So as long as has next returns true, like next, 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 you pull the items one by one, and then until the end. And what's going to happen is that when you do that here, it propagates all over and then orchestrates a whole flow of items through the runtime iterators, right, to compute the final one. This is the reason why it's called a runtime iterator tree. Now, if you look closer, there is a subtlety. There is a subtlety because I told you every expression in JSONic returns a sequence of items, right? But there are parts of JSONic that are not expressions. These are the clauses. In the FLWOR expression, we have the for clause, the let clause, the where clause, the count clause, the group by clause, the order by clause. These are not expressions. And you might remember that what they return instead are variable bindings, right? That we also call tuples. These are the things that looked a bit like data frames. So when you have a for or a where or a let and so on, you don't have sequences of items then. You have tuples or variable bindings. Tuple is just the W3C name for variable bindings, right? So instead, you flow variable bindings. So this is why here I put a different color. So in fact, in this iterator tree, you have most of the time sequences of items flowing. And in the special case of within a FLWOR expression, then you have tuple streams, variable bindings. For whom is that clear? Right? Okay. All right. But now, let me get into the details. Because if it were not an engine based on Spark, if it were, let's say, a previous generation engine, so there are a few engines that do that, then that will just stick to open has next, and you're done with it, and that's it. You release it, and you have an engine that is able to iterate. But if you want to bring parallelism and more optimization, you need to actually be more flexible than that. Because in fact, you have more than one way of executing or evaluating the same expression. And I'm going to show you now 3 ways. They are mathematically equivalent. They will give you the same results, but what's going on in the machines is not the same thing. So the first model that I'm going to give you is called the materialized execution. Materialized. Materialized means that I'm looking at one specific iterator here, more exactly at what's going on between the for iterator and the return iterator. So that's the output of the for clause that goes into the return clause, and that is a stream of tuples. Imagine that this you can take for granted. This is recursive, that comes from below, and from below you have a sequence of JSON objects, right? So this is the query I'm taking. You're basically reading from JSON file objects.jsonl. You're iterating and you're just navigating to the field. So what you would expect to get are the integers in there, right? For whom is that clear? Right, it's a very simple query. Now, what this iterator will do, if this is a materialized execution, is that this here is going to be materialized. It means that I take the first object that comes from here and I bind it to I. So this is the first binding, right? Then a second one, then the third one, and this one, and this one. Why am I saying it is materialized? I'm saying it's materialized because this actually is a structure that exists in the memory that looks exactly like this. You materialize it in memory and you have this in here, it's a list, but you can consider it more generally, let's say physically a data frame, right? This is materialized in the memory. You can actually look at the memory and you see that. And then you do the same here if you go further down, 1, 6, 4, 3, 2, and again, this is materialized. You have an actual list, an actual array with all the items in memory, right? So this is called the materialized execution when you do it like this. Can anybody tell me some drawbacks of the materialized execution, like the biggest drawback? Go ahead. It's sequential. So that is the first drawback. And do you have another one?
The memory usage.
And the memory usage. You're both right. These are 2 drawbacks. I'm going to focus for now on the memory usage because this is the one we're going to solve, and then we will solve the sequential aspect. So indeed, it takes a lot of memory because you really have to imagine if it's millions of objects that you have, or even billions of objects, that you're going to have in the memory this huge list with a billion of objects, this huge data frame with billions of records, and this huge list with billions of objects. That takes a lot of memory, right? So this is exactly the problem. How do we solve it? We solve it the Netflix way. When you watch Netflix, you don't download the whole series, well, except if you want to watch it offline, of course, but most people watch Netflix in a streaming fashion, right? You just download the next few seconds, and as you make your way through an episode, it's downloading the next seconds, but all the past episodes, they get thrown away, right? So it doesn't eat that much memory because you only need to have in memory the seconds that you're actually watching right now, right? This is why it's called streaming. And streaming is not only for Netflix, it's also for databases. So if you stream, then this is going to happen instead. I generate a first binding of I to field 1, and I immediately generate my first item that comes out of the return iterator, that is 1, it's the item 1. Then I generate a second binding, but you see what happens here. I threw away the first one. It's really like watching that Netflix episode and you already threw away what you've already watched. So now I have 6 here and I generate 6, 4, 4, 3, 3, 2, 2, and I'm done. Who sees that this eats less memory, right? This is exactly the goal. So think of Netflix, streaming, it's even the same world. And a drawback of this is exactly what you said, it takes time, because this is sequential. So you could actually process an unlimited number of items in this way. You could even process 1 trillion items or 1 quadrillion items because it doesn't stay in memory, right? So it doesn't matter, even if you have little memory, you could have 1 gigabyte of RAM and you could process 1 trillion of items this way. The problem is that you might still be here in 2 years if you try to do it sequentially like that, right? So this is the problem of this one, is that it can take a lot of time. And for this reason, what do? We batch, yes, and we parallelize, right? So the two of them, batch and parallelize, absolutely correct. So that means that now we get to use a data center where we have all of these machines. And what I'm going to do is that all of these objects that come from that file, they are basically spread all over the machines. You know how, because we studied HDFS. You know that HDFS is storing all of that in blocks of 128 megabytes that are spread all over the cluster. So in fact, what's beautiful is that when I'm saying we spread them all over the cluster, we don't even need to spread it. It's already spread. Because if it's in S3 or HDFS, it's already done that it's like this. So it is all over the machines. And then what we do is we process in parallel. So now I can get these data frames like this, but you know, it's only a sub-part of it, nicely in parallel. And then I get, again, in parallel. What I can do at the end is then write it back to HDFS or S3, then it's going to be sharded, right? This is going to be one file, this is going to be one file. Or if it's small enough, because I had some filtering, I could also collect it to a local list, right? So these are 3 examples. It materialized, streamed, and parallel. For whom is that clear? Right? Beautiful. So what's very important to understand here is that this is data independent in the sense that we don't really care which one is chosen. The results are always the same. It's always correct. So the only difference it makes is in terms of memory usage and the time that it's going to take to execute the query. And RumbleDB is going to do exactly that. It's going to arrange the choice between parallel, streamed, materialized, and so on, under the constraints that the results must be correct, right? The user should get correct results. But RumbleDB is going to try to make it as fast as possible by making decisions on whether parallel, streamed, and so on. A naive thinking might be we should always parallelize, but no, that's not true. If you parallelize for billions of items, yes, that makes sense. But there are cases where you're reading just a small file or you just have a few items. In that case, you should materialize or you should stream if it's very, very few items, because parallelizing has a fixed cost, right? If you parallelize, you have to instantiate the executors and so on. It takes a bit of time. So it's not always the case that parallelism actually wins. Okay. And of course, it takes a lot of machines, right, to do that. So the idea of RumbleDB, we renamed it to RumbleDB, by the way, just so that people find it on Google, because if you just find this, Pixar actually at some point released a movie with that name, and we were not even listed anymore. Yes?
So is it either parallel execution or streaming, or could it be also a combination of both?
A combination of both.
Okay.
In fact, within the same query, you can have everything. It's going to parallelize, and then it's going to materialize somewhere, and then parallelize again. It's totally able to do it in a hybrid fashion.
All right. Okay. Thank you.
In what cases would it make sense to use a stream execution but not parallelize and not materialize? Like if the data is small enough that you don't want to parallelize, why not just materialize?
That is a good question. So perhaps I would say that streaming has the advantage of flexibility and simplicity. If you have a small data but it starts growing, then it doesn't put a hard limit. So it means that you don't have, let's call it a singularity. You know, if you were always materializing, then you would basically have to handle a singularity, because if it fills the memory, then it suddenly crashes. When you use streaming, it has the advantage that it's not going to crash. It's going to take longer and longer and longer, but it's not going to crash. So this is why we stream whenever we want to avoid that singularity. That would be the intuition, I would say. Now, you're asking an excellent question, because basically, if I try to formalize this, if you would only consider, let's say, streaming and parallelism, and you try to find the break-even point, right? This is what we typically do in research papers, right? You basically plot, depending on the size of the data set, the time it takes to stream and the time it takes to parallelize. And then for small amounts of data, streaming is faster, and for large amount of data, parallel is faster, and then it crosses in the middle, right? Now you can do that for streaming and parallel, and you can do it for materialize in parallel. And now the formal question that you're asking is there any point in time in which streaming is actually both faster than materialize and than parallel, right? So this is something that I should think about that. Yeah. But does that make sense? The justification I gave, it's an intuition. Yeah.
Maybe one comment. I think there are cases where we need to be sequential for correctness. And then it makes sense to do streaming to have a few or a small memory usage. Whereas with parallelize, it would be incorrect. And if you just materialize, it would use a lot of memory.
Yeah, that might also play a role. Yeah. Right. So we're already going a lot into the details here, but I really need to think about that, because I hadn't thought of it this way. If there are cases where it's always worth materializing. All right. So RumbleDB allows you to query data on S3, on HDFS, on HTTP, on local file system, on Azure, and so on, of plenty of formats: JSON, CSV, Avro, Parquet, Roots, and so on, right? Now, more details about the implementations. There are cases, if you think of this static typing, sometimes you have the information that an expression is just going to return just one item or zero. In that case, you don't even need an iterator. It can be a simple method call. You call the method, get the result, and that's it. Right? So this is something we didn't have at the beginning. We were always iterating, but iterating when there's only one item is ridiculous. So we use a simple method call. Then when it's a few items, we can have this Volcano iterator. We iterate through them. And then you basically can use the same thing. If you have a filter here, you basically use a Volcano iterator that's going to iterate, execute the filter sequentially, then get a sequence here. So simple method call, Volcano iterator. there is no Spark in there. It's just pure Java. It's implemented in Java. It's pure Java, all right? Something that came to my mind because I'm still processing the question that you asked in the middle of thinking. The usage of memory also incurs a cost, allocating the memory and so on. When you want to allocate, let's say, a large array and so on, that also has a cost in memory. You have the Java garbage collection and so on and so on. So that, I think, would also play a role in the making a difference between streaming and materializing. Intuitively, I mean, as a database implementer, I really have the intuition that streaming is more lightweight and less costly than materializing. Right? Does it also make sense? Yeah. All right. I just thought of it while explaining that. All right. Now, so this is the case where it's local. What happens now when you start having a lot of data? So you read a file from HDFS. Let's say this is a JSON lines file, and it has, let's say, 1 billion objects. A JSON lines files is not necessarily valid against a schema. It could be a huge mess, right? So by default, if you're just reading a file and you have no idea if it's messy or not, you just make an RDD out of it, physically, internally, right? So RumbleDB is going to open that as an RDD in Spark. It's going to use basically a text file in Spark to get text. Then it's going to parse to JSON objects, and then to instances of item classes, right? And then you get an RDD of items. And here, we use the power of polymorphism. Have you heard of polymorphism in object-oriented programming? An item can be an object, an array, and so on. And Spark RDDs totally work with polymorphism. So this is why it works very well. And now we have an RDD of items in the memory. If I now have an expression that is the lookup, the navigation, I validate 2 countries, then what RumbleDB is going to do is use the flat map transformation, and it's going to use the flat map requires a lambda, right? Some function that is the mapping function, and for that we use what's called in Java a user-defined function. It means that whenever we use a flat map, RumbleDB is going to create some Java code that implements the mapping function. It's not totally trivial, but it involves the navigation to countries. That is all packed in a user-defined function that gets serialized over the network and broadcast to the whole cluster so that it can be executed on all machines in parallel. And then what you get is, again, an RDD of items, and again, polymorphic, right? You see a string, an array, and so on, but this is no problem at all for RumbleDB. Then you have this array unboxing. It's, again, all done with RDDs and using a flat map transformation. This time it's a UDF that does the unboxing. Then you get this, and that's how it's done, right? And then when you have functions, let's say distinct values, you want all the distinct values in there, this can also be pushed down to Spark. RumbleDB doesn't bother to compute the distinct values itself. It uses instead the distinct transformation in Spark to do that. So it's all pushed down to the cluster, and we use Spark to do the parallel execution. All right? So far, so good. Who is with me? All right. So now we have the local execution, we have the RDD execution, and then we have the data frame execution. When the data happens to be valid, for example, because we read a Parquet file, and then we have a schema in there, then it's preferable to use a data frame than an RDD because it's much smaller in memory. A data frame takes much less memory than an RDD. So what we do in that case is RumbleDB is going to use Spark to read the Parquet file and get a data frame out of it. Now it's no longer an RDD, it's a data frame, and you see the data is beautifully valid here. And then when you process it like you could navigate on it, then it's going to be a data frame transformation instead of an RDD transformation. What's very important is that all of that is physical. It's internal to RumbleDB. The user doesn't notice that. It only notices it's faster and that it takes less memory. But to the outside world, all we see is sequences of items. It doesn't matter if it's local, if it's RDDs, if it's data frames. That's just a physical detail. So to summarize, if we have heterogeneous data, we're going to physically internally use RDDs. If we have homogeneous data that is valid, then we are going to internally and physically use data frames. Okay? All right. So this is for handling sequences of items, right? Local execution, RDDs, data frames. What about FLWOR expressions? Because FLWOR expressions are like the most important expression in JSONic. It's the equivalent of the select from where in SQL, even more general. So whenever we have FLWOR expressions like this, by the way, the one at the bottom right gives you an example of this generalized SQL, right? Where you can have arbitrary sequences of clauses. Then we also need to process the variable bindings that flow from clause to clause. But this you already have an intuition about because you saw that these variable bindings, they already look like data frames where every column corresponds to a variable and every row corresponds to a variable binding. So this is the reason why we do also use data frames for the variable bindings, for the tuple streams between the clauses. So let's take an example. I have a JSON file here. I don't know if it's valid or not, so I'm just going to make an RDD out of it, right? Then it is in a for clause. So the for clause needs to generate a variable binding. At that point, there's only one variable, person, so it's just one column. And here, in that data frame, we need to put all of these objects. Now, we have a first challenge here, because normally data frames are structured. So if you naively think of it, that would only work if my data would be valid and homogeneous, right? But in fact, the trick is that you can turn all of these objects into bits, zeros and ones, and make the type of that column just a binary type. And what that means is that it's a bit of a performance penalty because you need to serialize 2 bits and then deserialize from bits back and forth between the items and the bits, but it works, right? And here, what you learn here is if the data is messy, performance penalty because of this. It's slower, but it still works. So we have an RDD, then we have a second for, right? Perhaps because we want to do a join or something. So this is going to be obtained with a transformation that adds a second column to the data frame. Because of my other variable, I have another column. And all of that, in fact, RumbleDB does with Spark SQL. RumbleDB generates Spark SQL queries internally. It's all hidden from the user on the fly to basically create this new data frame with this extra column. And then it continues where that's also going to be in Spark SQL with a where clause. So the where in JSONic translates to a where in SQL. Then you have a let that you can also handle with some SQL query, right? Adding a third column that is using an extended projection to do that. And then return is going to evaluate in parallel the expression. So in that case, $first name. And it's going to just keep $first name. That would be this, right? So that gets turned back into an RDD, right? So this is how it works internally. And again, the user doesn't see that. The user just types this, and then it's all going to be executed in parallel. So for the for clauses, if it's in parallel, we use data frames. But if it's very little data, and it's not enough to justify running in parallel, you can also have a local execution of the FLWOR expression. In that case, there won't be any data frames involved. It's just going to iterate. Next, 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 next. It just flows through the bindings. It can be streamed. It can be materialized. To give you an intuition, the for clause, we can stream it. The let clause, we can stream it. The where clause, we can stream it. The group by clause, we have to materialize it. The order by clause, we have to materialize it. Who has the intuition of why? Yes, can you tell us or anybody?
For group wise, you need to wait for all of the rows which fall into the group, and similarly for order by, it's sort of blocking in some way.
Exactly, that's exactly the idea. When you generate a group or something that comes out of group in a group by, you need data from many different places. And you never know if your group is complete. You really need to consume all of the data to be absolutely sure that it's complete. It's exactly the same reason why the shuffle part in Rumble, in MapReduce, the shuffle part can only, the reduce part can only start after the mapping part is over, the mapping phase, right? It's exactly the same idea. So for this reason, as soon as you have a group by clause and you execute it locally, then you have to materialize. There you don't have a choice, you cannot stream anymore. And the same goes for order by, because when you order, you really need to the entire data in order to know what the next tuple is going to be. So to summarize, here we stream or we materialize depending on the clauses. And what it translates to in parallel, when you would have to materialize here, that translates to shuffling, right? So if here you can stream, then that would be a narrow dependency here, and you can just group them in stages, right? As we explained with Spark. If here you need to materialize, then typically here it means you need to shuffle, right? So there is a connection between materializing and shuffling, and between streaming and narrow dependencies, right? Who has the intuition of that? If you don't have it yet, then think about it, right? Again, streaming narrow dependencies and materializing shuffling. There is a connection in there. And then for the expressions, it's what I already told you. You have the Java direct method call if it's just one item, like plus. You have the local iterations, next has next, and so on. You have the RDD transformations if it's messy, but parallel. You have the data frame transformations if it's valid data, it's sufficiently homogeneous. And we have one that I haven't told you about yet. It is that there are cases in which we do not even need to bother creating data frame transformations or whatever. We can literally compile the entire entire parts of the JSONic query in native Spark SQL, And that is the fastest that you can ever have when you're able to do that. Right. For example, this is a case where that is easy to do because this in SQL translates directly to foo +1. Yeah. Okay. So if I summarize a little bit, what's going on behind the scene is that we parse the query using G4 and LR, right? The compiler BAO. We create these abstract syntax tree and so on. At that point, we have a static context. It's basically all the variables you have in scope and so on, right? But you know at compile time. Then you statically infer the types. So you know if it's only one item, if it's more than one item, if it's an integer, if it's a sequence of objects and so on. Then you determine the execution mode. Is it parallel? Is it local? Is it just a method call? Is it native Spark SQL? Is it a data frame? Is it an RDD? It's also determined here at compile time. And then you create your runtime iterator tree, having already decided on what is parallel and not parallel. And then it's going to just be executed on the cluster. And as I said, that's the question you asked earlier. In the same query, it keeps going back and forth between local RDDs, data frames. It's fully hybrid. It just picks the best option depending on the knowledge, right? So this is a visual, the sort of things that you get. Again, for this query here, you get this runtime iterator tree. And really, you need to see, so here there's, that's the clauses, so there's streams of tuples. For the expressions, you have sequences of items. But look, here we do a simple method call. Here we use RDDs. Here we use data frames. Here we use data frames. Here it's an RDD. Here it's just a method call. It's a plus. Here it's a method call because there's only one item. Here it's a method call. And here it's a Volcano iterator. You see, in the same query, we use everything. And with the power of data independence, the user doesn't notice all of that. This is all hidden. Right. So here's an example of a very simple query that is just one line, so very easy to write for the user, but you see it's going to be RDDs all over the place, followed by a push down to Spark for computing the sum over billions of items. All right. So the general idea, now if I zoom out on what's going on in the community and in the database community, there is an ongoing convergence that has been happening now for a couple of years, and RumbleDB is aligned on that same idea. It used to be, I would say like 10 years ago, that there was really two kinds of database systems. There was the database systems for structured data, SQL, data warehousing, data cubes, and so on. And then there were the NoSQL systems, the cool ones with the startups and so on, so MongoDB, Couchbase, and so on and so on. And these two worlds were not really talking to each other, right? And Then something happened is that now people start merging this into a single system that can handle the whole spectrum. And the whole idea behind that, and the way that RumbleDB also works is, if the data happens to be homogeneous and nicely structured, it's just going to be magically faster. If the data is a bit messy and more heterogeneous and nested and so on, it still works, but it's going to be a bit slower, right? And so we see this convergence of systems. And there was an article in 2021 by the Databricks people, the ones who are behind Spark, who called that the data lake house. So a warehouse, this is for the data cubes and the highly structured data. A lake house is this idea of combining everything. You have a single system that has a data lake, that has unstructured data, a huge mess, and at the same time, it can construct structured reports and even involves machine learning and so on in the picture, right? So a single integrated system. So if who already heard of lake house? Okay, some of you. So this might be a word that is going to spread more into the community with time. It's already 3 years old now. Okay. So when we built RumbleDB, it was really the coolest part with all the students that worked on it. We did performance checks. We looked at, is it fast, is it slow, and so on. We compared it to other querying engines. And we found that it has a perfectly respectable performance compared to the other engines. So means that the students did a great work implementing all of that. And one of the very cool, that's my last slide. I just want to tell you what cool project we had. Also a master's student, Jan, who implemented machine learning inside RumbleDB. And here, the main idea was that I told you the items can be atomic items, object items, or array items, right? Then I said it can also be function items. And so the idea is to realize that machine learning models can just be put in the function items. And then you can write a JSON query where you take a data set, you can clean it up because it can deal with messiness, then you can validate the data and so on. And then you take from some library of machine learning transformers, and then you can just manipulate it using, where can I find an example? Yes, so you get an estimator that is k-means, for example, and then this is where you do the training. You basically feed the data inside the estimator, get a model out of it, and then you can take that model and again execute it. So here I did something very bad. I used the training set as a test set, but that's because I just wanted to write an example query. And you can basically call the resulting trained model on some other data, right? So it works very, very nicely in this ecosystem as well. This is obviously not material for the course, right? I'm just saying that this exists, and it was a really exciting master's thesis. Okay, I'm exactly on time. Do you have any questions? Anything that is unclear? All right. So I recommend you read the textbook, that you train yourself with the tutorials. There's plenty of JSONic tutorials that I shared in the course. There is also some online. Make sure you can write JSONic queries and that you practice it. This is really the best way. The TA team has prepared exercises for you. So thank you very much, everybody, for attending. I'm done with this. Next week, we'll talk about graph databases. The week after that, we'll talk about data cubes, and we'll even have some Oracle people who are going to come talk about vector databases in the context of LLMs. It's very exciting to consider also these shapes. So thank you very much. Thank you, Tobias, for moderating, and thank you for the great questions during the lecture. Have a great week. See you next Tuesday.